So today I'm going to start with the application of EMF measurement. Okay. Application of EMF measurement. This is the extension of the Nernst equation which we had done in the previous class. What is the Nernst equation? Nernst equation is E electrode is equal to E naught electrode minus RT by N ln of reduced state by oxidized state. Okay. What is E of electrode? It is the single electrode potential. Okay. What is E naught? Single electrode potential under the standard condition. What are the standard conditions? 1 molar solution and 25 degrees Celsius are the standard conditions. What is R? R is the gas constant, that is 8.314 joules per mole per Kelvin. And what is N? N is the number of moles of electrons involved in the electrochemical reaction. And F is the Faraday of electricity, that is known as 96,500 coulombs. Okay. So this is what we had studied, and in the previous class we had done the cationic electrode, anionic electrode, and how to calculate the EMF of the cell using the Nernst equation. So now going further ahead, the application of EMF measurement, which already we had done, we'll revise it and then go further ahead. We have seen that the application of EMF measurement can be done under two headings. The first one is calculation of thermodynamic quantity. Thermodynamics is that branch of chemistry which deals with the study of temperature during a reaction. Okay, during a reaction, how the temperature is going to change. That is seen by the thermodynamics. So we have different functions in thermodynamics. For example, enthalpy, entropy, Gibbs free energy, work function, system, surrounding, universe. All these are the different terminology used in thermodynamics. These are also known as the different functions of the thermodynamics. Under that, we get something known as G, which is known as the Gibbs free energy. Gibbs was the scientist who gave this free energy. And what do you understand by free energy? Free energy is the energy which is required to do useful work done. That is known as the Gibbs free energy. The energy which is required to do useful work done is known as the Gibbs free energy. So here, when I talk about the Gibbs free energy, we have a formula, delta G naught is equal to minus NF E naught. Here we can calculate the free energy of the cell reaction using our Nernst equation. If I talk about delta G naught, it is the standard Gibbs free energy. N is the number of moles of the number of moles which is taking part in the chemical reaction. F is the Faraday of electricity, that is 96,500 coulombs. E naught is the standard electrode potential of the cell. Standard condition, again let's revise, 25 degrees Celsius, 1 molar concentration or 1 atmospheric pressure if it is a gas. Then such type of delta G naught is known as the standard Gibbs free energy. Again, Gibbs free energy is the energy required to do useful work done. It is not calculating the wastage of energy. It is only the energy which is converted completely into work. That is known as Gibbs free energy. Now, this is for the standard condition. If suppose I have some other concentration, that is, it is not 1 molar, it is 1.5 molar or 2 molar or 3 molar, and the temperature is not maintained to 25 degrees, it is 26 degrees or 27 degrees, then at that time I cannot put delta G naught. I have to put it as delta G, which is only Gibbs free energy, not standard Gibbs free energy. And here I will not use E naught of the cell, I will just use E of the cell, which is what? E of the cell is my half cell electrode potential at any temperature and any concentration. So at that time, what my formula will become? Delta G is equal to minus NF E of cell. Okay. So these are the two formula by which you can actually calculate the Gibbs free energy. Okay. Now coming to the next, calculation of equilibrium constant. Now what is the equilibrium constant? Any reaction when you are having from a thermodynamic relationship, we know that delta G is equal to delta G naught minus RT ln Q. Okay. Delta G is equal to delta G naught plus RT ln Q. What is delta G? change in the Gibbs free energy at any temperature and any concentration. What is delta G naught? Standard Gibbs free energy. What is R? Gas constant, 8.314 joules per Kelvin per mole. Okay, what is T? Absolute temperature in degree Kelvin. And what is Q? Q is nothing but K equilibrium. What is K? K is the equilibrium constant. How did we calculate K equilibrium? Let's again go back to our basics. Okay, we had taken, let me show it like this here. Okay, we had taken one reaction, Na plus Mb gives Xc plus Yd. Okay, let me take, this is my reaction where N, M, X, Y are what? N, M, X, Y are the different moles of the reactants which are reacting to give different moles of the product. Now here when I apply the law of mass action, what will my K equilibrium become? My K equilibrium, that is, K is what? The equilibrium constant. K is what? The equilibrium constant. This K equilibrium will become, let me show it here, children. Yeah. Okay. K equilibrium will be equal to the product of the products divided by the product of the reactant. So I will write it like this, bracket C, bracket closed, okay, raised to the power X, okay, into, again, bracket D, bracket closed, raised to the power Y, divided by bracket A, bracket closed, raised to the power N, into bracket B, bracket closed, raised to the power N. Okay. So this is which equation? This is our equilibrium equation. Okay. Equilibrium equation is always calculated as the product, of the product. That is what product you are getting, product of the product raised to their respective powers, divided by product of the reactant. Reactant is A and B raised to their respective powers. So this is our law of mass action. Okay, in law of mass action. By doing this, we will get K equilibrium. K equilibrium is what? Equilibrium constant. Okay, it is a constant at a particular temperature. That K equilibrium is given as Q here. Okay, so what will be my delta G naught become? Delta G naught is equal to minus RT ln K equilibrium. Now, if I want to convert this log to the base e to log to the base 10, what do I have to do? I have to multiply it with 2.303. So, delta G naught is equal to minus 2.303 RT log K equilibrium. Again, then log K equilibrium will become what? Minus 2.303. I'll take it to the other side. Log K equilibrium will become delta G by 2.303 RT. This is log to the base 10. Only ln K equilibrium is equal to minus delta G naught by RT. Now, if I want to remove this ln, I have to take the antilog on the other side. So, antilog will be what? E to the power of minus delta G naught by RT. So, I'll get this expression. But I know what is delta G naught. From the previous slide, I know that delta G naught is equal to minus NF E naught. Substituting that value here in this equation, I will get what? Log K equilibrium is equal to NF E naught of the cell by 2.303 RT. So here if I take the antilog, K equilibrium will become antilog of NF E naught of the cell by 2.303. Taking the value F as 96,500, 2.303, 8.314, 298 Kelvin, and multiplying and dividing it properly, I'll get a value 0.059. So my final K equilibrium for any standard condition is equal to antilog of N E naught of the cell by 0.059 at 298 Kelvin. Again, let's understand what is K equilibrium? Equilibrium constant. What is N? Number of moles taking part in the reaction. What is E naught of the cell? Standard electrode potential. and 0.0591 at 298 Kelvin. By this formula, children, you can actually calculate the equilibrium constant of any cell. Okay. Any doubt here? No? Should I proceed further ahead?
Yes,
okay.
ma'am.
Okay. So let me go back. I'm a little bit slow with all these things. Bear with me. Okay. So let me read up this one. Coming back, children. I'm coming to the next one now, determination of pH using hydrogen electrode. Let's understand what is pH. pH is potence of hydrogen or power of hydrogen. Okay. What is a hydrogen electrode? Our hydrogen electrode is a standard hydrogen electrode or a reference electrode. Okay, standard hydrogen electrode or a reference electrode. How did we make the standard hydrogen electrode? We pumped hydrogen gas at 1 atmospheric pressure through a platinum wire and a platinum foil. And what was our electrolyte? It was 1 molar HCl solution. So what reaction was taking place? The H ion which are there in the solution, no? The H ion which are there. How did I get this H ion? HCl broke down into H positive and Cl negative. From there I got H ion. H ion accepted the electron and then it got converted into half hydrogen. That is 1 atmospheric. That is a liquid is getting converted into a gas. This reaction was taking place. It takes place in both the directions, forward as well as backward. Since it is taking place in both the directions, there is an equilibrium arrow mark which is put. This is our cell reaction for standard hydrogen electrode. Now here let's put our Nernst equation. What is our Nernst equation? E is equal to E naught minus 2.303 RT by F log of pH2 by pH1. Reduced state by oxidized state. Reduced state is gain of electron. Oxidized state is loss of electron. That's why H2 by H positive we got. What is E? Half electrode potential of half means hydrogen electrode. E naught standard hydrogen electrode 2.303. R is gas constant. T is absolute temperature. F is Faraday of electricity. pH2 is reduced state and H positive is oxidized state. Now we know that pH2 is what? We are sending hydrogen gas continuously at 1 atmosphere pressure. Since we are sending at 1 atmosphere pressure continuously, the pressure of hydrogen is 1. So 1 by H positive, I can take the H positive from the denominator to the numerator. If I am doing so, what is happening to my sign? The sign is changing from minus to positive. So what I will get? My Nernst equation will change to E is equal to E naught plus 2.303 RT by F log of H positive. Okay. But here, if it is a standard condition, again, standard condition, we should remember all these values, we should remember. Under standard condition, what do I have? R is 8.314, T is 298 Kelvin, F is 96,500. By multiplying and dividing, I get which value? 0.0591. Okay. And for standard condition, we always take hydrogen electrode as a reference electrode. And reference electrode has the value of what? 0.00 volts. Okay, since it is having E naught value as 0.00 volts, so what will happen to the E of cell? E of the cell is equal to directly 2.303 RT by F log of H positive. And by putting all the value, you get the value that at 25 degrees Celsius, when we maintain the temperature 25 degrees, the E electrode potential of cell at any concentration is equal to 0.059 log of H positive. So by using this formula, children, you can calculate the pH of the hydrogen electrode. Now you might be thinking there is no pH, then why ma'am is telling pH of the electrode can be calculated. Let's see further. So here you can see that I have taken the same expression, that is E is equal to 0.0 minus 0.059 minus log of H positive. Minus minus will become positive. And what is minus log H positive? Minus log H positive is nothing but pH. So potence of hydrogen or power of hydrogen can be given as negative logarithm of H positive ion. If I talk about POH, negative logarithm of OH ion. If I talk about pKa, negative logarithm of Ka. If I talk about pKb, negative logarithm of Kb. So any potence or power I have to calculate, I have to take the negative logarithm of that ion. So in this way, I am taking negative logarithm of H ion and I am getting what? I am getting pH. So in this way, my formula will change now. E is equal to minus 0.0591 pH at 25 degrees Celsius. Okay. So by this formula, I can calculate the pH of the cell. Let's take one example. Now I have taken on the left hand side, you can say left hand side is which one, children? Left hand side is your anode or cathode. Anyone? Left hand side is anode or cathode? Yes, I. Okay, he's having doubt. Okay. Left hand side is always anode, right hand side is always cathode. Okay, right hand side is always cathode, left hand side is always anode. So here I am having a hydrogen electrode which is acting as an anode. Here I am having the calomel electrode. Calomel electrode, you should understand KCl saturated solution, mercurous chloride and mercury is there. This is which electrode? This is the calomel electrode. So here, how will I calculate the EMF of the cell? We are having the formula. EMF of the cell is equal to E of right minus E of left. Okay, E of right minus E of left. E of right is what? E of right is my calomel electrode. E of left is what? My hydrogen electrode. You know the calomel electrode's value at 25 degrees Celsius and particular concentration, that is saturated solution of KCl, is constant. That is 0.2422 volt. This is a constant. Okay, we have to remember this. This is a constant. Then E of left hand side, the potential of hydrogen electrode from the previous derivation, we know what is it? Minus 0.0591 pH. So minus 0.0591 pH. This is for the left hand side. Taking these two value and substituting in this value, we get E is equal to E of right is what? 0.2422. 0.2422 we have substituted minus in the bracket of minus 0.0591 pH. Minus 0.0591 pH. Minus will become what? It can become positive also. If you don't want to change the negative sign and you want to just find out what is the pH value, take it to the other side. You get pH is equal to E. 0.2422 has gone to the left hand side, so it's become minus 2.2422, and minus it became positive, but here multiplication is there, so the other side it will get divided. So it will become 0.0591. By this formula, children, again you can calculate the pH by knowing the electrode potential of the cell. E is equal to minus 0.2422 by 0.0591. Okay, all these formulas we will be using in our numericals. Okay, on Monday we are going to do the numericals, and all of you get your scientific calculator, have a notebook and textbook, notebook and pen also, so that I will be giving you the problem and we will be solving it together. Okay. Now the fourth application is calculation of pH by quinhydron electrode. Again, quinhydron electrode, if you remember when we did in the lab, I had given you one small bottle which was having a black color powder. That was our hydroquinone. So when we were doing our titration, at that time we were taking the pinch of hydroquinone and we were dissolving it in HCl solution, and then we started with the conductometric and potentiometric titration. Okay. So what was the reaction which was taking place here? In quinone is having double bond O and double bond O. So two oxygen which are connected with double bond to a benzene ring, this is known as quinone. It will accept two electron and two H positive, and this double bond will become single bond. Here H will come, here also H will come, so it will become hydro, because hydrogen is joined, no? Hydroquinone. Okay. So rather than showing such a big formula, we can just write it as Q. Q is our quinone, and because it has joined how many hydrogen here? Two hydrogen. Since two hydrogen is joined, it is QH2. That is your hydroquinone. So while doing the derivation, we can use this one, Q and QH2. Q for quinone, QH2 for hydroquinone. So how can I calculate the pH by using the quinhydron electrode? Again, my Nernst equation. For everything, I'm going back to Nernst equation. Taking the foundation as Nernst equation, we are applying for different applications of the EMF. Okay, so Nernst equation is our base. Don't forget Nernst equation. Taking that, we are doing the different applications. So E is equal to again E naught minus 2.303 RT by 2F log QH2 divided by Q into H2. Now let's understand. E is what? The electrode potential of quinhydron. E naught is what? Standard electrode potential of quinhydron. R is what? Gas constant. T, absolute temperature. F, Faraday. Now you might be thinking, why this 2 is coming? Observe very carefully how many electrons they are accepting. 2 electrons. So that's the reason here you are getting 2. Okay. Log of QH2. QH2 is your product divided by Q into H raised to the power 2. Now again, why this 2 is coming? Look here. In the equation, can you see 2H positive? This 2 is the thing which is raised to the power. Whenever we use law of mass action, it is the product of the product divided by that of the reactant raised to their respective power. If suppose here quinhydron was 4, I had to raise it to the power 4. If here quinone was 3, I had to raise it to the power 3. So whatever number of moles are there, that will be raised to that power. Like this, we will write the equation. So again, here what will happen if I have to change, I have to bring the numerator to the denominator and denominator to the numerator. So what will I change here? I'll change the sign. So E naught plus 2.303 RT by 2F log of, the denominator has come to numerator, children. Observe here. So Q into H positive is per 2 divided by QH2. Now this equation I can divide it into 2 parts. Okay. H I can take it separately and Q by QH2 I can take it separately. So here I have divided it into 2 parts. Now here what is happening? 2.303 RT by F log of H ion. I have taken out this 2 and I have taken out this 2. So it has become F log H positive. Now continuing with this, because it is at equilibrium and this is a very weak acid, the quinone concentration of quinone. Whenever I talk about the box bracket is the molar concentration. Okay, molar concentration of quinone is equal to the molar concentration of quinhydron. Okay, quinhydron is what? Very weak acid. Very weak acid means partial ionization. Partial ionization means what? In the solution, you will mostly have the molecule and very less concentration of H ion. So what will happen to the pH? pH is almost, since it is a weak acid, it is less than 7, but almost nearing to the 7. Okay, due to the common ion. So what will happen to the log of Q by QH2? Because both are almost similar, no children. So here it will be, suppose it is 1 by 1, that is equal to log of 1 is equal to what? P. Whatever value is there, that will almost be similar, and log of 1 is always equal to 0. So the whole thing will become equal to 0. The previous equation we have now here, this will become equal to 0. So 0 multiplied by anything is 0. So what will this become? E is equal to E naught plus 2.303 RT by F log H positive. So it will get converted like this. Again, by taking standard condition and applying the value, remember 2.303 into 8.314 into 298 by 96,500 will become 0.0591 log of H positive. Okay. Now I want to take negative logarithm of H positive. Why I have to take negative logarithm of H positive? Then only I can calculate pH, no? So by taking the sign here minus and minus, the total thing will not change. Only to convert this negative logarithm of H positive, I can substitute the value pH. And here it will become E is equal to E naught minus 0.0591 pH. Okay. Here also you should remember, like for our calomel electrode, we had 0.2422. Here also for quinhydron, standard quinhydron electrode is 0.69964. Okay. By applying this value 0.6996 minus 0.0591 pH, pH can be calculated. Take the 0.6996 to the other side, 0.0591 to the denominator. This formula will give you the pH of any twin hydron electrode. So up till now, what we have done, we have taken hydrogen electrode, we have taken twin hydron electrode, and we have taken calomel electrode also, and we have calculated the different pH. Okay, let's take one example. Here what we are having on the left hand side, which electrode is there? This is the calomel electrode. On the right hand side, what do I have? On the right hand side, I have the twin hydron electrode. Again, what is my formula? EMF of the cell is equal to E right minus E left. E right is what, children? Cathode. E left is what? Anode. E right value is what? E naught minus 0.0591 pH. How did I get it? Let me go back. Here you can see 0.0591 pH. By this formula, I got it. Okay. So, and E left is what? This is a standard. For standard value, 0.2422 voltage. Substitute the value, and then you will get the pH that is equal to 0.4574 minus E of cell upon 0.0591. You can see how it is taking place. Here we have subtracted. Since we subtracted it, we got 0.4574. And by using this formula, I can get the pH of this combination of the cell. So it's very simple. It's just on your fingertips. Easily you can calculate the EMF of any cell. So don't panic. Okay, don't panic. It is very, very simple. Okay. So let's see another one. Determination of pH by glass electrode. So here we are talking about glass electrode. If you people remember, in our lab also we have used the glass electrode. Glass electrode looks something like this. Let me go back. Yeah, something like this. Let's understand. It is having a glass body. It's having a reference element here. There's a filling of buffered electrolyte. Mostly KCl is the buffered electrolyte. At the bottom, it is very, very delicate glass membrane is there. Okay. This is the glass electrode. Again, mostly in the center, you will be having some AgCl, that combination you can have. And then the bottom portion is very delicate because there only it will act as a semi-permeable membrane. It will act as a diaphragm, and the ions will go inside and come out through this combination. So this is glass electrode. Okay, this is one reference electrode. Reference electrode, like you can have a calomel electrode or a She, like that you can have it. Okay, and this is a combination electrode. This also you have seen in your lab, children. You have it. Combination electrode means I have a glass electrode also and the reference electrode also together. Means my anode and the cathode both are together. See the beauty of the instrument. Both of them are together, and that's the reason you don't have to take two electrodes and dip it in the solution. You can just work with one single electrode. So this is the new technology which the scientists have, engineers have done it, and this is known as the combination electrode. So again, coming back. So here the construction of the glass electrode consists of a glass bulb with a long neck made up of a special glass, relatively low melting point and high electrical conductivity. Again, the solution is 0.1 molar HCl solution, and saturated with twin hydron is filled up into the bulb. A platinum wire is placed in the solution to make the electrical contact, and the electrode is dipped in a solution whose pH is to be determined. So mostly your pH metry you can do by using this glass electrode. Let's understand here. On the right hand side, you can see, children, this is the calomel electrode. What was the calomel electrode? Mercury and mercurous chloride, Hg/Hg2Cl2. Okay, which is the saturated buffer solution here. KCl solution is there. Your mercury is there, and your mercurous is there, Hg2Cl2. Okay, the paste is there. This is our salt bridge. And on the left hand side, you can see this is our glass electrode. This is a very sensitive bulb. You are having a solution of 0.1 molar HCl inside the glass electrode, and outside any solution whose pH you want to determine. Okay, that is there, and it is connected to your system. So from here, how I can calculate the pH? Let's see. So on the left hand side, I had what? The glass electrode. What was the glass electrode having? Platinum, HCl, glass, and solution. Okay, that was the thing. On the right hand side, what did I have? I had my calomel electrode, KCl, HgCl2/Hg. Again, what is my EMF? E of right minus E of left. Who was E of right? Calomel electrode. Who is E of left? Glass electrode. Calomel electrode's value is how much? We know that 0.2422 volt is the calomel electrode. And left side glass electrode, just now we have taken the glass electrode value, E naught G minus 0.0591 log of H positive. Substitute the value, okay, open the bracket, it becomes minus E naught of G plus 0.0591 log H positive. Suppose I want to take negative logarithm of H positive, I'll take a negative thing, and this area will become what? My pH, protons of hydrogen or power of hydrogen. Then what will be 0.0591 pH? Take this to the other side, it will become 0.2422 minus E naught of the G. Take the 0.0591 to the denominator, I can calculate the pH of the cell, that is 0.2422 volt minus E naught of G by 0.059. Again, what is E? E is the electrode potential or the total electrode potential of the cell at any concentration, any temperature. What is E naught of the G? It is a standard electrode potential of the cell at 25 degrees and 1 molar concentration. Okay. Now this we had seen. Yeah. Okay. But there is a lot of advantage and few disadvantage also. What is the advantage of the glass cell, glass electrode is, whether it is an oxidizing agent, whether it is a reducing agent, the glass electrode will not react and it will act very easily with oxidizing and reducing agents, whether they are strong, whether they are weak. The other electrode, if we take, no, they will start reacting. For example, if I take a quinhydron electrode, what will happen? They start interfering with the oxidizing and the reducing agent. So rather than being a neutral or an inert substance, they will start reacting and they'll start giving wrong results. But glass electrode will be inert for all the strong oxidizing and reducing agents. That is one of the very, very important advantage of glass electrode. Second, you can use it in the presence of metal ion and poison. Now, if you remember when I taught you about standard hydrogen electrode, I said the hydrogen electrode will take lot of time to attain equilibrium. If little bit of arsenic impurity is there, the platinum will get corrupted. Once the platinum electrode will get poisoned or corrupted, the reaction will stop. So once the reaction is stopped, you have to start over all over again. So all those things will be taking place when your electrode is having any metal ion or poison. But here glass electrode will not interfere with any of these things. It will be very easy and nicely you can do it. And because it is cheap also and you can operate easily in the lab, almost all the college labs and the research education labs are having these glass electrodes. So these are the advantage of our glass electrode. But there is some disadvantage also. Okay, nobody is perfect in this world. No, everybody has their positive and negativity. So let's see the negativity of the glass electrode also. It's very, very, very delicate. So you have to handle it with care. It can't be used in the presence of a dehydrating agent. For example, concentrated H2SO4 has the capacity to absorb the water molecule. Once it absorbs the water molecule or ethyl alcohol will hydrate it, something like that will happen. No, all the HCl which is there inside the glass electrode will come out. And in this way, what will happen? The glass electrode will not be functional. Okay. Interference from sodium